I'm very passionate about concussion specifically, but also traumatic brain injury. And the difference being that all concussions are a traumatic brain injury, but not all traumatic brain injuries are a concussion, right? So this is the semantic game that we're playing right now, even in the concussion and sport group and the world consensus of concussion. We're really trying to define what's the difference between a mild traumatic brain injury, a concussion, and a traumatic brain injury. So when I say concussion, you should think mild traumatic brain injury because all concussions are a mild traumatic brain injury. And that's my area of passion. And the reason why I'm so passionate about it is because I feel like that it is grossly underestimated when we report its epidemiology and its incidence. When you start assessing and surveying high school students, it's been found that 1 out of every 2 high school students will admit to having the signs and symptoms of a concussion by the time they graduate. And when we ask them, why aren't they reporting it? Is they say, I didn't really know that it was a concussion, or I didn't really think it was serious enough to report it, or I didn't want to get pulled from my sporting activity. So the reporting of concussion is grossly underestimated, so much to the point that we believe by the time someone reaches middle age, let's say 30, 40 years old, that nearly every person has had a concussion at some point in their life, whether that be when they were a child, when it's more common, or it starts to become more common in geriatrics as well, too, because the fall incidence increases. So it's grossly underreported, therefore it's grossly underdiagnosed, therefore it's grossly undertreated. So when we start seeing individuals who have concussions, it's important to understand the mechanism behind it. When somebody sustains a concussion, what ends up happening is there's a whole bunch of activities that occur with inflammation and ATP changes, energy exchange insufficiencies. But the more important thing that happens is we start seeing remodeling of the brain. This is all good and great until there's increased demand, cognitive demand, stress, or increased activities, maybe looking at computer screens or reading. And then all of a sudden that person becomes symptomatic. So how does this dovetail into vagal nerve stimulation? Well, what we know, we've known this for over a decade now, and we're not really talking about it, is that vagal nerve stimulation helps remodel brain function. When you stimulate the vagus nerve, people often think that it's an outbound communication. We use the vagus nerve to communicate with our visceral organs to change our heart rate, our QR interval. We start looking at it as changing aspects of adrenal gland function, digestion, insulin release, all of these organ functions. But the majority of vagal nerve activation is actually afferent, going back into the brain. And research has shown through different types of viral tracers is that when you stimulate electronically or electrically the left vagus nerve, that we see a big activation in a part of our brain called our medulla and our brainstem, which then projects bilaterally to a very important part of our brain called the locus coeruleus. The locus coeruleus releases norepinephrine. Norepinephrine creates alertness, one of the 2 components required for neuroplasticity remodeling. You need to be alert and attentive to what's happening. We also know that those projections also activate the basal forebrain, which releases a very important neurotransmitter, a neuromodulator called acetylcholine. Now, acetylcholine is really important for creating new memories. So when you have alertness and attention and the substrate for creating new memories, then whatever happens with the confluence of those 2 neuromodulators becomes neuroplastic.